All right, so we're going to do our first example problem using Newton's second law in polar coordinates. So this is the very first question. I didn't do the example problem in the book because they already worked it out, so I feel that's kind of redundant, but again, it's an option. I feel this is a little easier though. Basically, we just have an astronaut in space, and he's twirling a mass m at the end of a string of length r. This is the string right here. Oops. In fact, I'll do it in a different color, maybe red. This is the string. And he's just swirling it around. It has length r, and it moves with a constant angular velocity omega. So omega is the same thing as what we said was our angle, the derivative of our angle, remember, from when we worked with circular motion. Omega, you might have seen it as d theta dt, but in this case we're just using phi instead of theta, and that's the same thing as the first time derivative of phi, just that's how we denote it. Okay, so we have that r, and we'll make a note that this is constant. And r, the radius, that we're also going to say is constant. The length of the rope isn't going to change, basically. Okay, so let's start with a good old free body diagram. And if we draw it for, just say, the picture we drew there, our little green bead, or whatever it is, the mass, it's like a ball or something. It's just a mass m. So this is our mass m. This is our mass m. There's no gravity because it's in space. There's no air resistance because it's in space. The only force is a tension force to the left. That's the only force acting on our block. Okay, well, the important thing to know is that tension acts parallel, that's this notation, the two lines means parallel, to our r. So in other words, tension is acting in the exact same plane, the same line, if you will, this bit right here. R lays on that little dotted line I drew, and so does tension. So when we do Newton's second law, if you remember from when we worked with polar coordinates, there's a force in our angular direction and in our radial direction. So we're interested in F sub r, which, again, we showed this in the last video, is mass times our acceleration. And this is our acceleration for F sub r, I'm sorry. Well, there's one force, so it's negative tension is equal to r staying constant, so r double dot is just the second derivative of r, but if there's nothing changing, this is just 0. That's equal to negative mr theta dot squared. If we divide both sides by negative, we'll finally get tension equals positive m. R in the book is big R, so that's what I'm going to change little r to big R. And omega dot, if you remember, we said, phi dot. I didn't mean to say omega. I might have been saying omega this whole time. I meant phi. Phi dot is just omega. So phi dot squared is just omega squared. There you go. This is the tension on the rope. So pretty straightforward example, not too hard. Might even do another problem today just because that one was incredibly quick, but I wanted to go ahead and do it.